There is a patch of sky, roughly 1.8 billion light-years across, that is colder than the laws of physics say it should be. 3 separate satellites over 2 decades have measured it, and none of them could explain it away. The leading serious explanation is that another universe brushed against ours. To understand why cosmologists are willing to entertain something that radical, you have to start with the oldest light in existence. In 2003, the WMAP satellite, NASA's Wilkinson Microwave Anisotropy Probe, completed its first map of the cosmic microwave background, the relic radiation from approximately 380,000 years after the Big Bang. The cosmic microwave background is the oldest light in the universe. It was emitted at the moment when the universe first cooled enough for electrons and protons to combine into neutral hydrogen, allowing photons to travel freely for the first time. The light has been traveling toward us, almost unimpeded, for 13.8 billion years. The temperature of that ancient light, when it arrives at Earth today, is approximately 2.725 Kelvin, a few degrees above absolute zero. The temperature is nearly uniform across the entire sky. The variations from one direction to another are tiny, about 1 part in 100,000. But the variations are not nothing. Here's the part that makes the anomaly serious. Those variations are how we know almost everything we know about the early universe. The pattern of slightly warmer and slightly cooler patches encodes the structure of the universe at the moment of its emission. By fitting cosmological models to that pattern, astronomers have measured the geometry of space, the composition of the universe, the density of dark matter, the rate of expansion. The cosmic microwave background is, in a sense, the most data-rich photograph ever taken. When WMAP produced its first complete map, the team analyzed it for any features that did not match theoretical predictions. The standard model of cosmology, inflation, dark matter, dark energy, makes very specific predictions about the statistical properties of the cosmic microwave background. The temperature variations should be Gaussian. They should be statistically isotropic. They should not contain any sharply defined regions that deviate strongly from the predicted distribution. The map contained a region that did exactly that. The region was located in the constellation Eridanus in the southern sky. Its center was approximately 10 degrees from the equator of the cosmic microwave background. The region was significantly colder than expected, about 70 microkelvin below the average, against an expected average variation of only about 18 microkelvin. The angular size was approximately 5 degrees across, which corresponds to a physical scale of approximately 1.8 billion light-years at the distance of the cosmic microwave background. The feature was unexpected. The feature was too cold, too large, and too well-defined to fit the predictions of standard inflationary cosmology. The team called it the cold spot. Within a few years, additional analyses confirmed the cold spot was statistically anomalous. Its existence violated the predictions of standard cosmology, with significance levels that, depending on the specific statistical test, ranged from a few percent to less than a part in 1,000. It was, by every measure, a feature that should not have been there, and astronomers had no explanation for it. In the 2 decades since the cold spot was first identified, many explanations have been proposed. None has been fully confirmed, and this is where each one, in turn, runs out. The first and simplest explanation is that the cold spot is a statistical accident. The cosmic microwave background contains many tiny fluctuations, and by chance, some of them will be larger and colder than typical. Detailed statistical analysis suggests this possibility is unlikely. The cold spot is too cold and too sharply defined to be a chance fluctuation, but it cannot be definitively ruled out. The second explanation is that the cold spot is caused by a foreground object between Earth and the cosmic microwave background. As cosmic microwave background photons travel toward us, they pass through the gravitational fields of intervening structures. If they pass through a large void, a region of low matter density, they lose energy, and the cosmic microwave background photons arriving from that direction appear slightly colder. This is known as the integrated Sachs-Wolfe effect, and it is a well-established phenomenon. The leading candidate for the foreground explanation is the Eridanus Supervoid, a vast region of low galaxy density, approximately 1 billion light-years across, located in the foreground of the cold spot direction. Initial estimates suggested the Eridanus Supervoid was large enough to account for a portion of the cold spot's anomalous temperature. However, more detailed measurements published in 2017 and 2024 indicate that the supervoid, while real, is not large enough or empty enough to account for the full magnitude of the cold spot. There is a temperature deficit that remains even after the supervoid contribution is accounted for. The remainder of the deficit, the part the supervoid cannot explain, is the part that has driven theorists to consider more exotic explanations. The third explanation is that the cold spot is the imprint of a parallel universe that collided with ours during the period of cosmic inflation. This sounds outlandish. It is not as outlandish as it sounds. Inflation, the period of exponential expansion in the first fraction of a second of the universe, has, in many theoretical formulations, a property called eternal inflation. In eternal inflation, the inflationary expansion does not stop everywhere simultaneously. Instead, it stops in localized bubbles, with each bubble becoming a separate universe. Our observable universe is one such bubble. There are, in this picture, an infinite number of other bubbles, expanding alongside ours in a larger metacosmic structure. If two such bubbles collided during inflation, the imprint of the collision would be preserved in the cosmic microwave background. The collision would manifest as a roughly circular region with an anomalous temperature signature, exactly the kind of feature the cold spot is. The size of the imprint depends on the timing of the collision and the geometry of the bubbles. A bubble collision in the early stages of inflation, when our bubble was small, could leave a feature roughly the angular size of the cold spot. The bubble collision hypothesis is not the leading explanation. Most cosmologists prefer simpler explanations, but it has not been ruled out, and it is taken seriously enough that several theoretical papers have explored the specific signatures a bubble collision would produce and how they might be distinguished from other anomalies. But none of that made the anomaly go away. The Planck satellite, which produced the highest precision map of the cosmic microwave background to date, confirmed the existence of the cold spot. The Planck data, analyzed in detail through the mid-2010s, reproduced the cold spot with extraordinary precision. The feature is real. The feature is too large to be a chance fluctuation at the simplest level of statistical analysis. The feature requires either an unusual foreground explanation, a modification of inflationary physics, or a deeper revision of cosmology. For most of the past 20 years, the cold spot has been considered an unresolved anomaly. It is not the only one in the cosmic microwave background. Other anomalies, the so-called axis of evil, the hemispheric asymmetry, the lack of large-angle correlations, have also been identified and remain unresolved. Each one is statistically marginal. Each one could, individually, be a chance fluctuation. But the accumulation of multiple anomalies in the same dataset has caused some cosmologists to suspect that the standard model of inflation is incomplete in ways that we are not yet capturing. The next generation of cosmic microwave background experiments, the Simons Observatory, currently being commissioned, and the proposed CMB-S4 experiment, will produce maps of the cosmic microwave background at substantially higher resolution and sensitivity than Planck. These observations, expected through the late 2020s and into the 2030s, will provide the data needed to either confirm the cold spot as a genuine cosmological feature or to refine its statistical significance to the point where simpler explanations become viable. In the meantime, the cold spot remains one of the most peculiar features of the universe we have ever observed. A region 1.8 billion light-years across, in the oldest light we can detect, that is colder than the laws of cosmology say it should be. There may be a simple explanation. There may be a profound explanation. Either way, the cold spot is staring back at us from the universe's youngest moments, and we still do not know what it is. The history of cosmology has been a history of anomalies that turned out to be either statistical curiosities or fundamental revelations. The cosmological constant was an anomaly. Dark matter was an anomaly. Dark energy was an anomaly. In each case, the field's initial reaction was to assume the standard explanation. And in each case, the standard explanation eventually failed, and a new component of the universe was added to the inventory. The cold spot may follow the same path. It may turn out to be a void slightly larger than current estimates. It may turn out to be a chance fluctuation. Or it may turn out to be the only piece of direct observational evidence for a structure beyond our observable universe. A fingerprint left by a collision that happened before our universe had cooled, before atoms had formed, before light could even travel freely. For now, there is a hole in the sky. We have measured it, we have photographed it, we have not explained it.